AP Chemistry. This is the last lesson in the Unit 14 Advanced Atomic Structure. It's called Molecular Orbital Theory. It's also the last part of your final exam, which for extra credit is due on Monday. I know that's not a long time from now, but remember, that's just for extra credit. The entire assignment is due on January 21st. But try to get as much done over the next few days as you can and get that in. Okay, the good news is this is a fairly short lesson, so let's go ahead and get started. So molecular orbital theory, which is abbreviated MOT, is an alternate way to view the bonding of atoms into molecules. MOT uses energy level diagrams as shown below. Now, you're going to see similarities to hybridization, but they're not the same theories. In fact, they're competing theories. And the developers of molecular orbital theory, there were several scientists who did that, and Linus Pauling and some others who promoted the hybridization theory were actually argued about whose theory was the better theory. And actually there are cases at advanced levels, so I can only report what I'm told, at advanced levels that molecular orbital theory is better, and others at advanced levels where hybridization theory is better. So it's just one of those things that there's no one perfect theory necessarily. So let's look at what we have here. So you have in this diagram, you have two boxes off to the sides. These are atomic orbital diagrams, and that's where you place the electrons for the atoms of for the electrons of the individual atoms. They go off to the side. Now, on top and bottom, you have the molecular orbitals. So the first ones were atomic. These are molecular. This is when they bond together to form molecules. So the molecular orbitals are placed in the middle of the diagram. Now the significance is not that they're in the middle. The significance is that one of them is up above the boxes for the atomic orbitals, those two on the side, and one of the boxes is down below. The box down below is called the bonding orbital. That is at lower energy than the two individual atoms that are being bonded. Remember, in chemistry, we've said this many times, that the chemical systems want to go to lower energy. Things in nature naturally want to go to lower energy. So if two atoms, when they bond together, can be at lower energy than they were as individual atoms, then they will want to bond. If by contrast, the two atoms, when you put them together, want to be at a higher energy than they were as individual atoms, they will not want to bond. That box up above, which says, let me read these designations here. That's sigma, the Greek letter sigma, 1s. So that's the bonding orbital for the 1s orbital. That's the one that hydrogen and helium have. Sigma means it's in between the two atoms. It's in the internuclear axis. We talked about sigma when we were talking about hybridization, so it has the same meaning. Now, that's the one that will bond the two atoms. The one up above is called sigma star. It's an asterisk, but we call it sigma star 1s. If the electrons go up there, they're going to be at higher energy than they were in the individual atoms, and that means they're not going to want to bond, or at least they're going to tend to not want to bond. It's possible it just makes the bond a little bit less or a little bit weaker, or it could be that they just don't bond at all. So down lower is good for bonding, because the electrons want to go down to lower energy level. Up higher is bad for bonding because that puts them at a higher energy. They're not going to come together to be at a higher energy. That's not going to happen. They're going to stay as individual atoms if that's the case. So the bonding orbital, the one at the bottom, is at a lower energy level than the energy level of the separate atoms. The bonding orbital is called the sigma 1s orbital for the first row. So again, that's hydrogen and helium. So molecular orbitals are filled from lowest to highest energy. The electrons first want to go to the lowest energy levels, and then they want to go to the highest. That's very much like the Aufbau principle that we talked about in the last lesson. They want to start at the bottom and work their way up to the top. An orbital at a higher energy level than the bonding atoms is called the Antibonding orbital, and it's given the symbol sigma star 1s for the first row. These asterisk star means anti-bonding. So bond order is a number that determines whether a bond will form between two atoms. The formula for bond order is that bond order equals the bonding electrons, the number of bonding electrons, minus the number of antibonding electrons divided by 2. You don't need to understand why that formula works, but that's just simply the formula that you need to know to calculate bond order, and you're going to see what that does here in a minute. So two atoms will bond if the bond order is a positive number, and the bond order number indicates the number of bonds. So if the bond order is 1, it's a single bond. If the bond order is 2, it's a double bond. If the bond order is 3, it's a triple bond. The physical structure of bonding and antibonding orbitals is shown below. So this is something new. You haven't seen orbitals that look like this before. But there you see we're talking strictly about the 1s orbital, the first row, hydrogen, helium. So there you have two hydrogen atoms, or let's say first they're two hydrogen atoms. Those are going to bond. We know hydrogen H2 bonds, and that's going to form the bonding orbital. That's the one you see down below. So there are the original hydrogen atoms, and that's a sigma bonding. The sigma bonding orbitals overlap. So they overlap to create a bond. Those two little dots are the nucleus. Okay, now if instead they're helium atoms, then they are not going to bond. We know that helium, a noble gas, doesn't bond with another helium atom. So this is the sigma star antibonding orbital, and they're separate. So if the two orbitals you see are separate, it means they're antibonding. If it's just one orbital put together like the one on the bottom, it's a bonding orbital. So example, show the molecular orbital theory diagram for the first row elements hydrogen and helium. So first we're going to start with hydrogen. There it is. So each hydrogen has one electron. And we have two of them, so we put them on opposite sides of the diagram. So what we're going to do is see if they form a hydrogen molecule in H2. So the first electron we take and we put down in the sigma 1s. The electrons always first want to go to lower energy level and then work their way up. The second hydrogen is going to do the same thing, so it's going to contribute that electron down there. It's going to flip over because it needs to have opposite spin. That's Pauli exclusion principle. So electrons know to do that. They'll just change their spin if they're with another electron of a particular spin. Okay, so that's it. We've used all the electrons. So there are two bonding electrons. And up at top, there aren't any antibonding electrons. So the bond order is going to be the bonding minus the antibonding divided by 2. So that's going to be 2 minus 0 divided by 2, which equals 1. So that means hydrogen does bond because it has a positive number for bond order, and that bond is going to be a single bond. So two hydrogen atoms will form a single bond. So this is not very hard. Let's see about helium. Okay, so here we go. There's helium. Now helium has 2 electrons. Each of the helium atoms has 2 electrons. So now they're going to build from the bottom up. So again, we contribute an electron there and from the other atom, and we've now filled the bonding orbital, the bonding 1s, the sigma 1s. But there's still 2 electrons left. So they have to go up to the higher energy level. So we put this one here. We put this one over here and change the spin on it. So now we've used all the electrons. So there are 2 bonding electrons down there, and now there are 2 anti-bonding electrons up top. So the bond order, there's the equation again, it's going to be 2 minus 2 divided by 2, which equals 0. So since the bond order is 0, the helium atoms do not bond. In order to indicate that there's a bond, the number has to be a positive integer number. So here's what's happening physically. 2 electrons of hydrogen can fit into the bonding orbital between the nuclei. This pulls the protons in the nuclei together to create a bond. So right there is the bonding orbital. And that's going to pull, those electrons in between are pulling on the protons in the nucleus of each hydrogen, and it's holding them together. So it's a perfect relationship in there. Now for helium, 4 electrons, because each helium has 2, that's a total of 4. 4 electrons cannot fit between the nuclei of the helium atoms. 2 of the electrons are going to be in a bonding orbital. That's what we saw in the previous diagram. And 2 move to the anti-bonding orbitals, which are on the outside there. And that pulls the nuclei apart from each other. Those 2 electrons on the outside are pulling on the protons in the nucleus, and that's weakening the bond. In fact, it's totally destroying the bond. So this results in no bond for helium. And the atoms get pulled apart. Okay, so let's look at when we get to the 2p now. So the bonding sigma 2p, that means that there are 2 orbitals on the sigma, on the x-axis. We said the x-axis is the sigma axis. It's the axis in between atoms. That's going to be the convention that we'll use for these lessons in this class. Again, other books could use y or z. We're going to use x. So the sigma 2p, that means the px orbital, which is on the x-axis, is going to be part of the bond. It's part of the sigma bond. Now, among the 2p orbitals, 2px, 2py, 2pz, one of these, we'll say it is the 2px, is on the internuclear axis and points at the other atom. So there you see it up there above. Notice it looks like those 2 bowling pins we talked about, those bowling pins, looks like 2 of them stuck together. And that's basically your sigma orbital. This is referred to as the sigma 2p orbital because a sigma bond is one that is on the internuclear axis and points toward the other atom. The sigma 2p orbital has a bonding and anti-bonding orbital, sigma 2, sigma star. It should say 2p there as well. So there you see the anti-bonding. You have the 2 bowling pins, but now they're pulled apart. There's a separation between them. So they're pulling on the nuclei and they're trying to pull them apart. And again, they might totally do that, or they might simply weaken the bond and make it still a bond, but less strong than it would be. The other 2p, those are the 2py and 2pz, are perpendicular to the internuclear axis and form pi bonds. So in other words, that's what we saw pi bonds are. They're the p orbitals up above or to the sides of the internuclear axis. They merge together and they form pi bonds. So there's one pi bond right there. Now the pi orbital has a bonding orbital above. That's the one we just talked about, and an anti-bonding orbital below. So you see what the anti-bonding orbital for those pi bonds looks like. Kind of looks like the bowling pins, and they're kind of bent around a little bit, but the important point is they're separated from each other, so they're pulling apart the atoms in the molecule. Okay, so now we're going to look at the 2p energy level diagram, and we'll discuss it in general, and then we'll talk about a couple of differences here. So these are for the 2p elements. That would be boron, carbon, nitrogen, oxygen, fluorine, and neon. So let's look at the energy level over on the energy diagram over on the left. Let's just start with that one. So don't worry too much about the sigma 2 pi x, sigma 2px, sigma 2py, pi 2pz. Just understand the energy levels. I would memorize those. I would ask you to memorize those. And what you got to understand is that each of those boxes, each of those squares can hold 2 electrons, just like with the Aufbau, an up arrow and a down arrow. So if we have 2 elements there in the middle, and we'll assume that they're the same 2 elements, then each one contributes an electron to the 2px and the the sigma 2px and the sigma 2py down at the bottom. Each one contributes 2, so that fills up that orbital. Then, if they have enough electrons, if it's one of the elements towards the end of the 2p, they can fill up the pi 2pz. So those would be bonding orbitals because they're below the middle of that diagram. That's where the atoms would be as individual atoms. If it goes above that, if they continue to have electrons, they're going to start filling up the pi star 2px and the pi star 2by. That's in the middle up towards the top. And that can hold 4 electrons. Each one of those can hold 2. If there's still electrons, so we'd be talking about neon at this point, then they would fill up the sigma star 2pz. Okay? The diagram on the right, it's the same ordering. It's just you start at the bottom and each square gets 2 electrons. Okay? And you fill it up the same way as we did Aufbau, up arrow, and then down arrow, down arrow. Now, here's a difference here, and I want you to have this memorized. Right, the diagram on the left is for boron, carbon, and nitrogen. The diagram on the right is for oxygen, fluorine, and neon. And you'll notice that they're not identical. Down there, what you see in the red box, the bonding orbitals are reversed. So they are flipped around, and also their names are changed somewhat. So the 2 boxes that are side by side on the left, they are sigma px, sigma py. On the right, when they get flipped up above, they're pi 2x and pi 2p. You don't need to understand this. Again, sometimes it's important to know what you need to understand and what you don't need to understand. You don't need to understand this. You just need to be sure that when you draw the diagram, you use the correct one of these diagrams. If it's boron, carbon, or nitrogen, you use the diagram on the left. If it's oxygen, fluorine, or neon, you use the diagram on the right. Your assignment is going to be each question, and I'm only going to give you 4, well, a couple more, but the 2 that are already in this video. So I'm only going to give you 4 to do on your own. And that is, you're going to be sure that you draw the right one. Okay, it doesn't take that long to draw these. You don't have to make them pretty, just make them relatively neat. So down in the yellow box below it says the bonding 2p bonding orbitals are reversed between the boron carbon nitrogen diagram and the oxygen fluorine neon. So just be sure you use the correct diagram. Okay, so now we're going to fill up the 1s and 2s orbitals. So there are the electrons. Now this would be the configuration for beryllium. You have 2 atoms down at the bottom. You have a filled 1s subshell, I should say. And then you have a filled 2s subshell. That would be beryllium, element number 4. So we can go ahead and place the electrons here, just as we did before. We're filling up the 1s subshell. Again, that has nothing to do with bonding of second row elements, so you know it's going to be filled. Its bond order is 0 if you just look at the 1s, and therefore it's not a part of the bonding. Now we're going to go ahead and fill up the 2s, and again you build from the bottom up, and there we go. So those are 2 bonding electrons, 2 anti-bonding electrons, 2 bonding electrons, 2 anti-bonding electrons. So there's the formula. You have 4 bonding minus 4 anti-bonding divided by 2. That gives you 0. So this is the 1s and 2s configuration for beryllium and for all 2p elements beyond beryllium. So that means that the 1s and 2s never become involved in the bonding of 2p elements. So this means the 1s and 2s electrons do not contribute to the bonding of 2p elements. So now let's actually look at lithium and compare it to beryllium here. Okay, so here's lithium first. It has 3 electrons. It's number 3 on the periodic table. 2 of those are in the 1s orbital. That doesn't play a role in bonding. And the other 2 are the single electrons that a lithium has in its 2s orbital. Okay, so look at the periodic table. It's got 1 electron in its valence orbital. That's the 2s. So each lithium atom contributes 2 electrons to the 1s subshell, which is not involved in bonding of 2s elements. So we'll go ahead and put those in again. Those go up to the anti-bonding. The first 2 were bonding, now they're anti-bonding. So you have 2 minus 2 is 0 for the 1s. Then each atom contributes 1 2s electron, both go into the sigma 2s. That's the bonding orbital. There it is. And you're done with the electrons. You're out of electrons, so there's none to go up above in the sigma star 2s, the antibonding orbital. So no electrons go into the sigma star 2s, so the bonding order is, there's bonding, there's antibonding, and there's bonding. So the bonding order is, there's the formula again, it's 4 minus 2, 4 bonding versus 2 antibonding, and that gives you 1. So what does that mean? It means there's a bond, and it also means that the lithium molecule, L2, has a bond order of 1 and will form a single bond. That's what the bond order tells you, is how many bonds you will have. Okay, example, draw an energy level for nitrogen, for a nitrogen molecule. So nitrogen is the third element over in the 2p subshell. It's the fifth element over in the second row, but it's the third in the 2p subshell. There's boron, carbon, and then nitrogen. So you're going to put together 2 nitrogen atoms. So you got to be sure you use the correct diagram. So that's the correct diagram for nitrogen. Those are bonding orbitals. Up there, those are anti-bonding orbitals. They're up at a higher energy level than those 3 boxes on each side, which is where the individual nitrogen atoms will be. Okay, there's the electrons. So nitrogen has 3 electrons in its 2p orbital. That's why there's 3 electrons there. We're only looking at the 2p. We've already dealt with the 1s and the 2s. So this is just the 2p. There's 3 electrons there for nitrogen. So now we're going to start placing them. Okay, and there we are. So we've used up all the electrons in the 2p. We see 6 electrons, and we can see that they're all 6 are in bonding orbitals down below. There weren't enough to go up to the anti-bonding orbitals, so all 6 are in the bonding. So there are 2 anti-bonding electrons in the 1s and 2s and 2 anti-bonding electrons in the 2s for a total of 4 anti-bonding electrons. Okay, so that's where all the antibonding electrons are, is in the 1s and 2s. You don't see that on the screen, that's on the previous slide. There are 2 bonding electrons from the 1s and 2 bonding electrons from the 2s, so again, that's 4. So the 1s and 2s are a wash. They don't affect this. Now we're getting to this energy diagram. There are 6 bonding electrons and no antibonding electrons in the second orbital. So the bond order is going to be 10. 2 from the 1s, 2 from the 2s, and 6 from the 2p here. That's a total of 10. The antibonding, is, we've already said, is 4. 2 from the 1s, 2 from the 2s. So 10 minus 4 is 6. 6 divided by 2 is 3. So N2 forms a triple bond. From previous lessons, we learned that an N2 molecule has the Lewis dot structure. There you see it below. It has a triple bond. Okay, example, draw the energy level diagram for an O2 molecule. So there's the energy level diagram. Now you use the other one. You use the one for oxygen, fluorine, and neon. Be sure you use the correct diagram. So I'm going to have you draw these as part of the assignment. It doesn't take that long. Draw them and label them. Okay, so there you have 3 boxes on each side. In this case, we're interested in oxygen. So how many electrons does oxygen have in the 2p orbital? It has 2 in the 1s and 2 in the 2s, but in the 2p, how many? It's the 4th element over in the 2p subshell, so that means it's going to have 4 electrons in the p orbital. So we'll go ahead and place those. Well, first we'll show you the bonding and anti-bonding orbitals. Now we'll go ahead and place the electrons. There they are. Up, 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 and then you start pairing up with a downspin electron in each of those. So again, those are 2 identical oxygen atoms. Now we start placing them. Okay, so now we filled up the bonding orbitals down below the atom level, the atomic level, the middle there. So now the last two have to go in antibonding orbitals. So as with nitrogen, there are two antibonding electrons in the 1s orbital and two antibonding electrons in the 2s orbital for a total of 4 antibonding electrons. Again, you don't see that on the screen here. That's the previous slide. There are also 2 bonding electrons from the 1s and 2 bonding electrons from the 2s orbital. Again, you have 4 and 4, so those even out. Now down here, there are 6 bonding electrons. There you see them there, down on the bottom. And 2 antibonding electrons, there you see those, up at the top. So in all, you have 10 bonding electrons in total and 6 antibonding electrons. 2 from the 1s, 2 from the 2s, and the 2 that you see right there up above in the pi star 2px and pi star 2py. So there's your equation. You do the math on that and you get 2. So this oxygen forms a double bond. That should be a double bond down there. And from previous lessons, we learned that O2 molecule has the Lewis dot structure that you see there. It has a double bond. We know that. We've done that one before. All right, that takes care of this lesson on molecular orbital theory and the last lesson for this unit and the last part of your winter final exam. So I'm getting it out to you on Friday. If you've been doing the lessons as I put them out, then you're up on that. If not, that's okay. I'm going to put answers. It's not going to be complete answers, okay? I expect you to watch the videos and pick up the things that are right there in the video. I'm not going to give those to you. So go ahead and get this done. If you can get it done by Monday, it's extra credit, but even if you can't, it's due on January the 21st. So enjoy the rest of your holiday. I look forward to seeing you next week.